So I'm a PhD student here at Edinburgh. I'm going to talk today about the impact of wind power on energy storage revenue. So quickly, what I'm going to talk about today, a bit about my motivation behind why I'm talking about energy storage, looking at what the commercial opportunities are for energy storage, and then looking at a little bit more detail in how electricity prices are formed and what might happen in the future if we have a large amount of wind power in our system. Hopefully, if I don't get the nod from Adam, I'll have time to present some of my preliminary results as well. So firstly, what I'm talking about, I'm talking about large-scale multi-megawatt, multi-megawatt-hour range grid-connected electrical energy storage. So this is things like pumped hydro schemes, compressed air energy storage, potentially liquid air in the future, or large-scale batteries. I'm not talking about anything that's smaller scale, nothing for portable applications, not talking about transportation, anything for power conditionings, island application, gas storage, seasonal storage. That's all for another day. So moving on, why am I talking about energy storage? So globally we're faced with the challenge of the energy trilemma, which is the issue of balancing sustainability, security and affordability in our energy supply systems. And electrical energy storage has been cited as one of the potential solutions to this challenge, in that it can enable a large amount of intermittent renewable power to be connected to the grid. So there's a number of benefits that electrical energy storage can bring, so a few of them highlighted here. Haven't got time to talk about them all, but research has shown that by 2050 we could expect that electrical energy storage could bring savings of £10 billion per year to the electricity market in the UK. So I'm going to be talking particularly about the UK today. So that's all good and well, but how do you actually access those savings? And in order to do that, you need to have commercial opportunities for storage, so you need it to be a viable option for people to invest in and make money out of. Otherwise we won't make those savings. So there are a few ways in which energy storage can make money. I'll just run through a couple of them here. So first one, through transmission and distribution upgrade deferral. This is not without its problems. So companies face high penalties for having poor reliability in this part of the market, and so they're particularly risk averse. This means that they tend not to want to invest in new technology, and they tend to stick to tried and tested technologies, so energy storage isn't really that appealing to them. Furthermore, on the regulated side of the electricity market, there's quite complex ownership models in terms of whether DNOs or TSOs can own generating equipment, which is what electricity storage is classed as, so it makes it even less appealing. You could provide ancillary services, so things like black start services and stuff like that, but again here you're competing with existing technologies which have already had decades to come down their cost curve, and so when you introduce new technologies you find that actually they can't compete on a cost basis. So finally we can look at arbitrage, which is time shifting energy, and this is what I'd like to talk in a bit more deep about. So this is a time series of electricity prices. I think this is in November 2007, I'm going to say, so a week. First week in November, and you can see that there are opportunities to buy electricity when the prices are low, and you can then sell your electricity when the price is high. So it looks like there should be opportunities to make money out of storage this way. But when you start taking into account technical constraints, storage efficiencies, conversion efficiencies, and then start looking at what the capital costs are of storage, you soon find that in current markets you actually can't make enough money to pay back your costs. So to understand why this is, we can take a little bit of a more detailed look at what's driving electricity prices. So this graph shows the peak electricity prices over a year. So this is for 2005, so I've taken the maximum electricity price for each day and plotted that. And if we plot on the same graph what the gas price is for the same year, you can actually see they follow quite a similar pattern. So as we'd expect, because we have a large amount of gas generation equipment in the UK, gas prices tend to influence what the peak electricity price is. And if we come back to looking at the weekly cycle, and we plot what our electricity demand does over that same week, we can see that on a daily basis electricity prices tend to follow what the same pattern as demand follows. So we know that electricity prices are being principally driven by gas price and by electricity demand. And if we plot on this same graph, so we've got the scale up the side here is power, so that's what the demand is plotted on, what the wind was doing, and what wind power output was in the UK for that period, you can see it's really quite a small proportion. So wind's not really making a significant contribution to electricity at the moment. So this leads us to some interesting research questions, such as what would happen in the future if we did have a large amount of wind power in the system? Would you have more volatile electricity prices? And if you did, would this mean there would be more opportunities for arbitrage? And could you make your money back on electricity storage? So that's what my research is looking at. So to understand what's going on, we need to look at how electricity prices are formed. And this is a kind of simplified stack model. So we assume that our generators in the UK are split broadly into 4 classes of generation. We've got nuclear coal, combined cycle gas turbine and open cycle gas turbine. And we assume that they get dispatched in order of their lowest marginal generating cost. So we've got various inputs that go into this graph. We've got the generator capacity sets how far along we have of each generator. And then feeding into our marginal generation cost, we've got fuel costs, carbon costs, performance characteristics. So that shows what the marginal costs of generators are. And what we find actually happens in a competitive market situation is you get generators that bid to produce electricity at a price that's between their own marginal generating cost and the cost of the next marginal generator. So we assume a hyperbolic function between these 2 points, and we start to form a supply curve for how electricity prices will be formed. When you get to peaking plant, which is up here, there's no upper limit on what prices could be bid. And what you actually find is competitively they're aware of this. So obviously as supply gets scarce, you tend to get extremely inflated electricity prices. And this represents how much scarcity there is in the system. So we model this with an exponential uplift function for up here. So we've got this light blue curve now which shows what our electricity price supply function looks like. So once we know our supply function, we can look at what our electricity demand is at any point in time, and from that read off what the demand is, what the price would be, and we can get an output of what our electricity price time series might look like. Gets slightly more complicated when you start introducing renewable energy into the system. So conceptually I've modelled here the UK as a single bus network, which is obviously quite a vast simplification, but it's a common approach used here, and it's been shown to be reasonably valid for historic data. So what we do is we take a time series of the renewable energy output, which I've taken from some work which has been done here at Edinburgh University by Lucy Pradden, and subtract that from the demand time series and assume that that's then how much dispatchable power we need our thermal generators to meet. So instead of just taking our demand and seeing where it intersects our supply function, instead we take our required dispatchable power, where that intersects the supply function, we then read off the electricity price. So once we have our model set up, this is just some basic validation results. So this shows the model simulated prices are here in red over this week, and the historic prices are shown in blue. So you can see it shows reasonably good representation of what's actually happening. You're generally within about 10%, you've obviously got a few exceptions here where it's not quite right. I've obviously picked a very nice week to show you that the results line up nicely for. So I validated the model over a 3-year period. So we looked at prices for January to the end of December 2005 to the end of 2007. And you can see here, this is the monthly average electricity price. So we can see we're getting a reasonable following of what the shape of electricity prices did actually do. So once we know what our electricity price model is doing, and it's doing roughly what we want it to do, we can look at what might happen in the future. So looking at the future is an interesting thing. Obviously no one knows what's going to happen. So the approach that I've taken is to use scenario modelling. And the National Grid have defined 4 different electricity scenarios that they look at, based on different levels of sustainability that might happen in the future and different levels of affordability. So we have in the top right corner here our gone green scenario, which is the most sustainable and assumes the quickest economic recovery. So this is what I've used to look at some results. So this is a scenario where we have a lot of emphasis on renewable energy, we have a lot of available cash invested in novel technologies. So it's basically the most positive situation for wind power, so it's a way of looking at what the most extreme case might be. So to run through how the model works with future scenarios, we've taken our demand time series. The way that I've modelled this is at the moment using a historic time series of demand and scaling that up to match future peak demand and future average demand. This is something that I'd like to look at a bit more in the future in terms of how demand patterns change, because we're just assuming that demand behaviours will remain the same in the future, which maybe might not be the case. But for a first starting point, it's not a bad way to go. For renewable energy output, we take a similar assumption. We've taken wind speed profiles from historic years and assumed that our installed capacity in the UK is scaled up at the same sites as it is currently to represent the future spatial distribution of wind turbines in the UK. Again, this is probably a reasonable assumption for onshore, but offshore we're probably looking at a slightly different distribution of what we have at the moment, so this is something I'd like to look at in the future. We then have our supply function with all our things feeding in, so we've got future generator capacities, that's an input from the future scenarios. Generally the performance characteristics are kept the same as historic data, and then we have future fuel costs and future carbon costs, which are all based on what the scenario inputs are for the gone green scenario. From this we get a time series of electricity prices for what a future year might look like, and We can then look at what our storage characteristics are, and based on that determine what our optimum strategy would be for operating our storage and how we can maximise our revenue. So the results that I'm looking at here, I've assumed a 200 megawatt hour capacity of storage with a 20 megawatt power rating and a 75% efficiency. So that's looking at characteristics that might be similar to a very small pumped hydro station, or the kind of scale of technologies that compressed air might be coming in at a demonstration scale. So, on to some results. Still got a bit of time. This graph shows the annual revenue which is available for this electricity storage device from 2020 up to 2025. And you can see that there's increasing revenue, which is good. We know that we're increasing our wind power year on year. So we start to think that actually wind power might be good for storage. This is using the 2006 wind speed profile and demand profiles and scaled up. But if we actually look at what the installed wind capacity was doing, so this is plotted on the scale on the right, we can see that we've increased our wind capacity from over here in 2020, it's around about 22 gigawatts, up to over 40 gigawatts. So for such a huge increase in wind capacity, we're getting really quite a modest increase in storage revenue. So you start to wonder if actually it's something else that's driving it, and if it's not the wind capacity at all. What's more, if we then plot the revenue which was available from 2006 electricity prices, again, we see there's not that much of an increase from 2006 to 2020. And if we plot right down here, this was what the installed capacity was in 2006 of wind, around about 2 gigawatts. So you start to think that maybe it's not wind that's driving these increases. And when you go back and look at some of the underlying factors that are changing in the gone green scenario, what you actually find is that the capacity margins are changing, and also the gas prices are changing. And what you find is that the scenario assumptions assume that between 2006 and 2020, you only actually have a small increase in gas price. Then once after 2020, the gas price starts to rise. We assume that there's countries like China and India are increasing their gas demand, so globally, gas prices are increasing. So what we find actually is that this is probably more likely to be driven by the gas price than it is by the wind power. What's another interesting result is if we then plot the same results but using a 2007 wind speed profile instead of a 2006 wind speed profile, we find that our revenue just about halves. And that's really interesting, because what it means for storage revenue is that in the future, if you have a large amount of wind installed, from one year to the next, you don't know what your revenue is going to be. You could expect it around about the £1 million mark one year, and then if you have a different wind profile the next year, you're only actually getting around about £500,000. So this is actually not good for storage, and investors don't want to see this kind of fluctuating revenue. Interestingly enough, 2007 was actually a windier year than 2006. So we start to think that actually when you have more wind blowing in a system where you have more wind capacity, you actually get reduced revenue. And that's an interesting result, and it's one that I didn't expect to be one of the outcomes. So if we take a look at why that's happening, this shows the last couple of months, so November and December 2025, based on the 2007 wind speed profiles. So we've got demand up here, which is very similar to what it would look like today. And then we have our wind power output. And this is an interesting time because we have a couple of weeks in December where there's very low wind output, and the rest of the time where there's quite high wind power output. If we sum these together, so we do our demand subtract our wind to figure out what our dispatchable power requirements are, you do see that you get a hugely more volatile time series, and this is what thermal generators are trying to do to match. So you would expect there'd be more opportunity for storage, you would expect there'd be more volatility and more chance to buy and sell at different prices. But when you plot what the electricity price is doing for the same period, what you actually see is you get some volatility, you get these uplift in prices where you rely on your peaking plant, but where you have these periods where high wind power interacts with low demand, you actually get the prices suppressed. So you get these additional periods which you wouldn't have seen if you didn't have wind power in the system, of suppressed electricity prices. And what that means for storage is that you have a lot more opportunity where you can buy energy when it's cheap, but a lot less when you can sell. So I just had the nod, so on to my conclusions. Increased wind power leads to more suppressed electricity prices, but actually fewer periods of inflated electricity prices, and other factors maintain a significant influence on electricity price, including thermal plant capacity and fuel prices. So additionally, wind is more likely to cause higher variation in arbitrage revenue year on year, and in fact we conclude that wind power may in fact be detrimental to storage revenue. So for some further work I mentioned previously, I'd like to have a look at how the demand behaviour might change in the future and what wind farm distribution might look like. Alternative future energy scenarios, also have a look at alternative storage devices, and how changes to the electricity price formation might happen in the future with various different incentives from the government, like the electricity market reform capacity mechanism. Thank you very much.
Okay, so thanks Anna for a very interesting talk. We'd like to invite any questions from judges or the wider audience. So, Camilla?
Hi. For those of you who don't know me, I also work with Gareth, so I do like a bit of an input on Anna's work. But your work comes up to, your historic work comes up to 2007.
Yeah.
And you've shown some trace between the electricity and gas prices up to that time. Have you got the potential to take it slightly further forward? Because my most recent research seems to be showing that there's been quite a dramatic change since 2008 in what's forming prices with regards to coal, because the coal prices worldwide have fallen quite dramatically.
Okay, so there is the potential to do that. The reason I actually used 2005 to 2007 to look at was because that was the data that I had most readily available. So I've got daily gas prices for that period. It probably would be possible to get it for more up-to-date periods, but I kind of managed to get that, and it took me long enough to get the data that I thought, right, I'll work with what I've got first. But certainly that's something.
And do you think that would have an impact on the future scenarios, or are they all moving away from gas, moving away from coal?
No, they're not actually. The future energy scenarios that the National Grid have proposed, they change them every year. So last year they only had 2 future energy scenarios, and actually this year they've got 4, and then they'll redo them next summer as well. So I've kind of picked this year as ones to look at for now. But they have, the majority of them move towards phasing out coal, but they do have some scenarios. I think it's the no progress scenario where they do have coal still remains a part of the electricity system. So they do look at those as well.
So the question off the back, and then we'll get to the front.
Thanks, Anna. Did your figures include the reduction in constraint payments for wind as a credit to having storage?
No, I don't. So that's something that I haven't looked at all. So in my modelling work, I've assumed we just have a single bus network. All the wind power can always be used, and it's not constrained until the entire UK demand is met. But the figures that I produced at the beginning, the savings of £10 billion a year to the electricity system, that's some work by some people in Imperial College, and that took into account constraint savings and looked at, if you look at the system as a whole, where the savings come from, and that did take it into account.
And please, what is the approximate capital expenditure for this 200 megawatt?
So for something like this, I originally had the data in this report, and I actually took it out because it's so uncertain. The figures in literature vary hugely, but so from the lowest estimate to the highest estimate of what I found for a device this size, you get quotes from around 10 million up to 100 million. The 10 million mark, I've only seen one source that says that, so they tend to be more 50 million and above. So that's the kind of prices that you're looking at.
Quick one from Franz, and then a quick one from a judge.
First of all, it's my economic topic, but to ask you, Austria don't have any atomic power plants, and you have that. So if there's a revision of an atomic plant, we sort of have a huge drop down in power. So is your research to be done for? I have only seen 1 year, and you told us that there's sort of a gap in the beginning of the year because of wind power. Have you done this for more than 1 year, or is this only for a year? Your research? So because of this, if there are sort of maintenance work, then you sort of.
So I'm not quite sure that I understand.
I'm not quite sure if I can follow your research because of, is this only to be done for 1 year or for more than 1 year?
So I'm
drop down in power you told us.
So Anna, I think it's to do with the change in the base load generation mix, is that correct? So how sensitive would the results be?
For how many years are the results, or have you compared more than 1 year?
So I've got my model set up to run for the number of years that I have input data for. So the future energy scenarios run from today up to 2035. So I have data for every year up to there. But in terms of using the historic data and which time series I'm using, we have wind speed profiles at Edinburgh from 2005 up to 2010. So I can use any of those wind speed profiles to look at what's happening and what's changing. So I mean, I've only just started to get these results out, so I will intend on running it for more years.
Yes,
But it's just what I have at the
this
moment.
diagram, yeah, have you compared this from
I
one
think
to one? So that
we'll need to take this one offline because we're running over. But it's a good question. We need a question from Sasha, from one of the judges.
Thanks for the presentation, but I would like you to add a few comments and then
Okay.
ask one question. What we know based on the forecasting is that demand is expected not to increase significantly
Yeah.
in the next years.
Mhm.
Having opportunistic bidding based on the price will be certainly influenced, as you said, in some of your scenarios, which will shift peak demand. So any opportunity for that will most likely reduce in time.
Yeah.
So we have reduced demand, reduced difference between the peak and minimum demand. And I'm wondering, have you tried in this analysis to size the energy storage with respect to some, let's say, variations in the wind profile over the, let's say, wider region where you have smaller wind resources, or allocate energy storage to a bigger wind farm or wind farms, in which case you will prevent any penalty in bidding because there was no wind, although it was forecasted, or prevent any curtailment if they are producing more. So that would be an interesting addition. Have you considered that?
Yeah.
Not just opportunistic, but let's make
Yeah.
the system more.
I haven't at the moment. The reason I haven't is because I was trying to look at it purely from a commercial point of view, so coming at it from more of a bottom-up approach. So we know that you have got system value, but actually looking at where the incentive is in terms of how you make money. But I know there is some research that's going into sizing stuff and matching it with wind turbines, so it's something that I'll look into a bit more in the future. Thank you.
Thanks. So if we thank Anne again for
This production is brought to you by the University of Edinburgh.